Here we're going to talk about how we deal with electron configurations of ions. We'll start with the main group elements and how we deal with ions of D block elements, so transition metals. We treat them just a little bit differently. So we're familiar with electron configuration of something like helium, 1s2 configuration, and then ns2 NP6 valence electron configurations for other noble gases as well. That tends to be quite stable, so a lot of these ions will preferentially have ns2 NP6. Hydrogen and helium are a little different. They will just have the 1s. They prefer just 2 electrons, so 1s2. These main group elements will either lose or gain electrons in order to achieve the same number of electrons as the nearest noble gas, and therefore have the same electron configuration as that noble gas. This will be how we can justify the trends in charges that we're already familiar with. So this is the reasoning behind why group 1 tends to be a +1 cation, for example, and all of the other examples we've seen. Species that have identical electron configurations are called isoelectronic series. So you can have a number of different ions that actually have the same number of electrons, so they will have the same electron configuration, though that does not mean that they're identical. There are notable differences because they may be different elements, they may have different charges, so on and so forth. So to write an electron configuration of an ion formed by a main group element, we're going to write down the configuration for the atom, and then based on the charge, you're going to add electrons or remove electrons as needed to match the charge. So if we take a look at sodium and chloride here, so first we'll write sodium in its ground state, and once we form it a cation, sodium plus, that is the removal of 1 electron. So the 3s1 electron is taken away when we are writing sodium plus. And now you can see that we have that ns2 np6 electron configuration for Na plus for sodium. That it's the 2s2 2p6. So we only had 1 valence electron, the 3s1, that was removed to form its most stable cation, which is Na plus. Chloride is a little different. Instead of taking away an electron, we're adding an electron. So chlorine in its neutral state is 3s2 3p5 for its valence electrons. Going to chloride, you are adding 1 electron to become negatively charged. So now we again have that filled S and P outer valence electron shell, very similar to a noble gas. So 3s2 3p6 is its final electron configuration. So this is some justification for why we know sodium preferentially is a +1 charge and chloride preferentially is a -1 charge. As a somewhat of a shortcut, we can choose to write electron configurations for ions using the noble gas core, which is what we had done also in the past for noble gas cores. But a lot of times that means the electron configuration is just the noble gas core. So for example, sodium in its ground state is neon plus the 3s1. Sodium plus, once you remove that electron, has the same electron configuration as neon. So you can just write it in brackets as neon. Really important here, that does not mean that it is neon. So you can represent an electron configuration as bracket neon, but that does not mean that it's neon or the same as neon or chemically similar to neon or anything like that. But it does mean that it has the same number of electrons and the same electron configuration as neon. Chloride, we can do the same thing. Chlorine, once you add that outermost electron to it, it will be neon plus 3s2 3p6. I will often leave it as neon 3s2 3p6. Though you can decide to change it to showing that it is the same as argon. Oftentimes I leave it as neon 3s2 3p6 because that is the valence shell that has recently had electrons added to it. So it's sometimes just a little clearer to write it that way, but either are fine. And it does show that you again have a noble gas configuration of argon. So let's try some of these. Let's write electron configurations for the following ions of main group elements. So I would preferentially first write the electron configuration of the atoms, then add electrons if it's anionic, or remove electrons for cations to account for those charges. The setup here, N3 minus, there's the electron configuration for nitrogen, barium, and beryllium. And then for nitrogen, we're adding 3 electrons, so we will end with 2s2, 2p6. For barium and beryllium, we're losing those s2 electrons. So this is what we'd end up getting, and you can see that each of these have a noble gas configuration. Again, for A, I would sometimes just keep it the way it was and show helium 2s2, 2p6, though it does have a configuration of neon. So D block elements we treat a little bit differently. We might expect the 2 electrons lost when we're forming iron 2+ to come from the D subshell, since it is a D block element. Actually, though, we end up losing electrons first from the shell with the highest value N. So what's kind of strange about that first row of the transition metals is they have electron configurations that start with 4s2, but then that first d orbital that you hit is a 3d orbital. So it's actually a lower principal quantum number than the prior s orbital. So if you take a look at iron, the 4s orbital is a little bit higher in energy. It's 4s. So in that ground state electron configuration, it's argon plus 4s2, and then that first d orbital you hit is actually 3d6. So this is the electron configuration for iron. If we're going to take away 2 electrons, like this is stating, we actually end up taking away the 4s2 electrons first and foremost. So a lot of transition metals commonly actually have a +2 charge associated with them, and that's because of the loss of both of these s electrons, since all of those, or I should say many of those transition metals have 2 s electrons. Some of them have a different ground state electron configuration that wouldn't necessarily be predicted with the periodic table. So here you can see iron 2+ is argon 3d6. As a minor note, I also put in here iron 2+, argon 4s0 3d6. Sometimes people will put in 4s0 just to note that they didn't leave those out, since it's kind of buried interior to that. It's showing very explicitly that those 4s electrons were the electrons that were lost in the formation of iron 2+. I mildly prefer this when I'm doing it, but by and large, I don't think that this is very common.